So last time I started giving an example of deformation quantization in a genuine Poisson case. So that was the so-called Poincare-Berthel-Witt quantization. That is, we use Poincare-Berthel-Witt theorem and construct a map from symmetric algebra of a Lie algebra to the universal enveloping algebra of the same Lie algebra as linear spaces. So if I denote this isomorphism by sigma, then the star product, the Poincare-Berthel-Witt quantization, takes two elements f and g in a symmetric algebra of G, and then defines the product by the formula the inverse of sigma f dot sigma G. Thanks. Here, dot denotes the product in the universal enveloping algebra. And well, there is the Homo variable h bar is missing from this notation, right? So I explained last time how one can actually introduce it into the play. But now it remains to prove that this is in fact the deformation quantization formula in the sense which I explained last time, right? So there are a few things we need to prove. So yeah, if you want to introduce h bar, you need to introduce h bar here, multiply these by h bar, and that's more or less it. And extend sigma to an h bar linear isomorphism, but that's more or less this. Need to show that first the star product is associative, but that's almost evident from the formula. But that's not enough. We also need to show that, well, the star product of f and g can be written in a form of formal power series beginning with the usual product of f and g. Then the first term here will look like h bar divided by 2, the Poisson bracket of f and g. And the Poisson bracket is the standard Kirillov-Kostanz-Fourier bracket on the dual space of Lie algebra, right? And the remaining part is given by some formal sum of bidifferential operators bk acting on f and g. Right, formal power sum for k from say 2 to infinity. It is infinite, but of course for all f and g polynomial, so f and g from a symmetric algebra, this sum will be finite. Right? So what I really need to prove, I need to prove the existence of some universal bidifferential operators, and that will also allow me to extend my formula from usual polynomials to the smooth functions, right? Okay, and then number 3, you can sometimes add the condition that f star 1 is equal to f and is equal to 1 star f. So also you can sometimes add the condition that bk of fg is symmetric or skew symmetric depending on the dimension of k, on k. So in fact, number 3 is actually the simplest thing to prove. Number 3, right? Because you can just check that if this map sigma sends 1 to 1, and of course the formula follows immediately. So this is simple. Associativity is also simple. As far as the first term in the product is concerned, and as far as the second term in the product is concerned, I started proving this last time, and actually you can either prove this by direct computation, which is somewhat tedious, but I'll show this direct computation a bit later, but you can also do this by some abstract universal construction. Actually, it depends on how well you know the Poincare-Hall-Beat theorem. There is a way you can formulate Poincare-Hall-Beat theorem which actually explains the first two terms in this formula very easily, very well. So first, I need to introduce the filtration on the universal enveloping algebra. Namely, I'll say that an element at Fk, the space of elements of filtration K in UG, is equal to the image of the tensors of degree less or equal to K in the universal enveloping algebra, right? You probably remember that universal enveloping algebra is equal to the quotient of the tensor algebra of G by the relation that x tensor y minus y tensor x is equal to the commutator of x and y, right? So here you just take not all the algebra, not all tensor algebra, but just the part which consists of tensors of degree less or equal to k, and that is your Fk. Of course, Fk of UG contains Fk minus 1 of UG, and so on until you get to F0 of UG, which is just the ground field. And of course, the union of all Fk's of UG is equal to UG, just because every element has some finite filtration by definition of universal enveloping algebra. We also see, and that is easy, that the product of Fk UG by Fl UG, that is, if you take any elements in Fk and Fl and take their product, what you will get will belong to Fk plus L of UG. Right. So this allows you to define the so-called graded algebra associated with the filtration. Whenever you have an algebra with some filtration in it, you can define filtered algebra associated with this filtration, and that is in this case just the direct sum for k from 0 to infinity Fk plus 1 of UG divided by Fk of UG. And yeah, probably you also need to add F0 because F0 does not show up here. And that's not very important, but still to make it clear, right? Then this is in fact an algebra due to this condition due to this condition. Because if you take any element, so if this is G K plus 1 of G, right? You take any element F bar here and G bar in G L plus 1 G, right? Then their product will be well defined. I mean, you just take the elements which belong to the corresponding filtrations, which represent F bar and G bar. And then you define the product of F bar times G bar as the image of the product of F times G under this map, right? This element has some filtration, so you take its filtration and send it to the quotient. By the way, the map which associates to every element in UG its image under this in this algebra is not a linear map. So you should be very careful when you define it. But it is well defined in any case, and this product is associative, almost evidently, right? And you can also check that this product is also commutative. F bar times G bar will be equal to G bar times F bar. In fact, one way to formulate the Poincare-Verhofstadt theorem would be to say that this algebra is in fact isomorphic as algebra to the symmetric algebra of G. Right.
Okay. I got a little bit lost in the motivation. Like why did we start seeing the filtration and then the graded algebra? I understand everything here, but why?
What is the purpose?
Yes.
I really want to show that the star product of F and G, which I defined, would begin with F times G plus H bar divided by 2, the Poisson bracket of F and G. I really would love to say this. And the easiest way, in my opinion, to prove this would be to redefine the Poisson bracket. Actually, I'm going to give another definition of the Poisson bracket right now, explain why this Poisson bracket is in fact equal to the Kirillov-Kostantsuriov bracket, which we worked with already. And then it will be evident that this star product I defined will begin with this Poisson bracket at the first stage. Okay? So that's just a kind of a shortcut I'm making. And also I take this opportunity to recall you some properties from the Lie theory, some facts from Lie theory. So yeah, so one way to formulate the Poincare-Verhofstadt theorem is to say that the graded algebra of UG is isomorphic as algebra to the symmetric algebra of G. In this case, we can actually now define. So probably better to use bars now in a bit different way, right? With your permission, I'll move bar from left to right. Right. And here I use the brackets to denote the image of the elements in the universal enveloping algebra under this projection to the graded algebra. So now you have two elements F and G. How can you define the Poisson bracket? So if you take F and G, you first find elements f bar and g bar in the universal enveloping algebra, which represent them, right? Then you take the commutator of f bar and g bar in the sense of universal enveloping algebra. That is to take f bar times g bar minus g bar times f bar, right? It follows immediately from the Poincare-Berkhov-Witt theorem. It follows immediately that
Those bar elements simply belong to our gradient.
to the universal enveloping. I'm sorry, I thought it would be probably more convenient to denote by bar, by f bar, the element universal enveloping algebra, which represents f.
So this bar and this bar are not connected.
They are the same. What do you mean not connected? So if you have an element f here, an element g here, and you can choose f bar and g bar in universal enveloping algebra, which will represent these two elements, right? And then I define the product of f and g here in the graded algebra by the formula. I take their representatives, f bar, g bar, take their product in the universal enveloping algebra, and take the image of this element in the graded part, right? And then you'll see that this is true. This is one of the possible ways to formulate Poincare-Berkhov-Witt theorem. I just wonder whether you have seen this or not.
Okay.
It's more or less the standard way to formulate. So now I use this construction to introduce the Poisson bracket on the symmetric algebra. So I take f and g, take their representatives in the universal enveloping algebra, right? Then I take the commutator of these elements. Now, since this algebra is actually commutative, as I explained, this commutator will have filtration not equal to the sum of filtrations f bar and g of f bar and g bar. This element will have, this commutator will have filtration equal to the filtration of f plus filtration of g minus 1. Is this clear? So, okay, if you need more explanation, I can give it. Okay. This is a pure algebra. I just wonder whether you've seen this construction before or not. Because sometimes people formulate Poincare-Berkhov-Witt theorem in this way. So I wonder whether you have seen it or not. Who else have? You haven't. Okay. I mean, this is a natural, this is a very standard way to formulate Poincare-Berkhov-Witt theorem.
But it is without the grading.
Okay, so let me... Okay, that means that I need to make some digression into pure algebra. Okay, then. It seems that I need to make some digression in algebra. Okay. I try to skip this and to be fast, but, you know, sometimes the fastest way to do something is the slowest one. So, so suppose you have an algebra. A is an algebra, an associative algebra. We say that A that has an increase in filtration is given an increasing filtration if F can if A can be represented as the union from 0 to infinity of some subspaces fi of a, such that usually one asks that f0 is equal just to the ground field, ground ring. And then we also have fi of a is inside fi plus 1 of a, and so on. Yeah, so that's what they call the increasing filtration. Then, so in this case, and also, we assume, of course, all these spaces, all these sets are actually subspaces for all I. Fi of a is a subspace, and for all I and j, fi a times fj a is inside fi plus j of a. So that's what they call the filtered algebra. When you have a filtered algebra, you can in fact do the following trick. You take any two neighboring parts of filtration, stages of filtration, and take their quotient. You can do this because of these inclusions. And then you take the sum for I from 0 to infinity and call this the graded sub f of a. For every element f in this graded sub f of a, we denote by f bar the element in A such that first f is in some, this is direct sum, so f belongs to some, we can assume that f is actually homogeneous, right? When we have a direct sum, we can assume that the element is homogeneous in the sense it belongs to some graded component completely. If it's not homogeneous, you can just decompose it into homogeneous parts. Then you take f bar in A such that f bar belongs to fi A, and the projection of f bar moduli fi minus 1 of A is equal to f. You can always find this representative. Then you can do the same thing with f in ith graded component of A, right? Let's put it I, and g in jth graded component of A. And then you define their product f times g as the product of f bar times g bar modulo f I plus j minus 1 of A. And this product is well defined because every element f bar and g bar is well defined up to the addition of certain elements of lower filtration, right? So when you take the product of elements with lower filtration, you end up here and up. So this product is well defined, and this gives you the structure of algebra, of graded algebra here. Graded in the sense that whenever you take two elements here, then this element will actually belong to graded sub f of a of degree I plus j. Right? Then the Poincare-Berthov-Witt theorem can be actually formulated as follows. If you take the standard filtration on the universal enveloping algebra, the filtration induced from the standard gradient on tensors, on tensor algebra, then the associated graded algebra will be isomorphic to the symmetric algebra of G. This is one way to formulate the Poincare-Berthov-Witt theorem. I just wonder whether you have seen this. This is often explained at the course of Lie theory. So I hope you have seen this already.
How is it related to the basis in universal enveloping?
What do you mean?
Like initially, in our course, the formulation was about the basis.
It depends on how you define it.
So
But actually, there is okay, if you really want, I can go, but today I'm not prepared to give the proof of Poincare-Berthov-Witt theorem in full. I probably, yeah, by the way, I'm going to prove Poincare-Berthov-Witt theorem still for you, but in totally different setting and with totally different methods. And you'll see that this will be true. Okay. But yeah. It will be some cheating, of course, but everything in this world is a cheating. So now, since we can actually identify the symmetric algebra with the graded algebra of universal enveloping, right? You can now introduce the Poisson bracket here by the following construction. You take f in Sg of degree I. Again, you assume that f and g are homogeneous. G in Sg of degree j. Take their product, take their representatives, and take the commutator of these representatives. That is to take, say you take f bar g bar minus g bar f bar. It follows from this equality that the filtration of this element will be not I plus j, as one could expect, but in fact it will be at least 1 degree lower, because the top degree elements, they cancel out due to the fact that in top degree we have commutative product, right? So now you define the Poisson bracket of f and g to be equal to the image of this commutator, but this time you take it modular f I plus j minus 2. You go further down in the degrees, right? Now again, you can easily see that this is well defined, because whenever you add elements of degree f minus I minus 1 or j minus 1, then the commutator will be even lower than I plus j minus 1, or filtration of even lower than I plus j minus 1. It will be of degree I plus j minus 2 at most. So this is well defined again. It is well defined. And you can easily see that all the conditions of Poisson brackets are verified by this operation. First of all, of course, f comma g is equal to minus g comma f, right? That's because the commutator is skew-symmetric. More important, it is that this operation actually verifies the Leibniz rule. That is to say, we have this formula. And that's true because whenever you, well, first of all, if you take an element representing G times H, by this definition, you can assume that the element representing G times H is in fact equal to G bar times H bar. After this, you can just use the fact that the commutator verifies Leibniz rule. And that's all, more or less. And finally, the Jacobi identity for the brackets follows from the Jacobi identity for the commutator. So you actually have this Poisson bracket. In order to show that this Poisson bracket in fact coincides with the Poisson bracket we defined, it is sufficient to check that this Poisson bracket coincides with the given one on linear functions. You see, f and g, they are polynomials of degrees I and j, right? But if I and j are equal to 1, both, then you can easily go through all these definitions and see that the commutator of x and y of degree 1 is just given by their Lie bracket. And now it is easy, well, I think we already discussed this, but you can actually check it yourself if you have forgotten, that these four conditions uniquely define the Poisson bracket on polynomial algebra SG. So it means that this bracket we have coincides with the Kirillov-Koston-Suryo bracket. Okay? That's the way you can reproduce the Kirillov-Koston-Suryo bracket from the abstract construction. It follows almost from the definitions that it follows almost immediately from the definitions that if you take f and g in SG and take their star product in both directions, right? So this is given by sigma minus first of sigma f sigma g minus sigma g times sigma f. And then up to degree 1, you'll get just the Poisson bracket, like this. It does not mean, of course, that the first element in the star product has this form. I mean the second element, of course. But very shortly I'll explain why, but at least I'll shortly explain that at least it means that what we have, this star product, can be, by some equivalence map, be brought to this. So we can actually replace the star product. If we don't have this identity at the nose, but we do, we can do it, bring it back here by some equivalence relation. So that actually closes the second property. And it only remains to show that this subproduct is given by some universal formula. This gives me, I'm going to sketch the proof right now. And the main purpose for this is that it gives me the opportunity to bring forward some beautiful identity in universal enveloping algebras discovered by Felix Berezin. I think I have write it in Russian. Let me write down this formula. Suppose you have an element x in G, which you of course embed into the universal enveloping algebra. And then you also have the symmetrized image of x1 through xp, certain elements in the Lie algebra, right? Then you can ask how one can compute the product of x in the universal enveloping algebra, the product of x and this symmetrized xp. And here is the formula. It is equal to first x, x1, xp plus sum j from 1 to p minus 1 to the power j by j factorial and multiplied by bj. Bj is the Bernoulli number. Okay, the j is Bernoulli number. It's some rational number which doesn't depend on any choices made. So then we need to sum up over all possible sets of indices R1, Rj inside the indices from 1 to p. Yeah? And what we have here is sigma of commutator x, x R1, comma x R2, comma x Rj times x1, then we have x R1 omitted, and so on until we get to, of course, all xrj's, xr, I don't know, k probably, are omitted. J from the notation. And that's all. So if we now look on this formula from this point of view, right, it will only mean, of course, this is equal just to the symmetrization of x, right? So you can actually now rewrite this formula as follows. When you apply sigma minus first to it, you get x star x1 xp, right? So on the right you'll have just x times x1 xp plus, now when you apply sigma minus first to this, it just disappears. But what you have, this you can replace by the Poisson bracket of x1, x and xr1, right? And so on. So what you get will be some sum will be a sum with some coefficients of following form. Right? But what does it mean, this sum? For instance, what does it mean, the sum over all possible R1 of the form x, x R1, x1, x R1 omitted, xp. It's just equal to the Poisson bracket of x and x1, xp, right? So this is definitely by differential operator. Moreover, it's just the Poisson bracket, which I promised, right? Also, if you take the second element here, and it will look like x, xr1, xr2, x1, xr1, xr2, xp. Then you can actually write it as, again, as some kind of differential operator. For instance, we take okay, how do you write it as differential operator? I mean, here you can write it as pi ij x d dx1 d dxi d dxj applied to x xr1, right? And then you also have pi I pq, probably ab, d dx a applied to this, d dx b applied to r2, right? So you now can expand all these formulas and and get something like, yeah, on the right you'll have, in the end you'll have d dx r1 d dx r2 applied to x1 xp, right? So if you use this, you get something very, which is, we get some formula in terms of differential operators. So this formula actually means that the product of x and any monomial is given by some universal set of differential operators. These differential operators, they don't depend on this, on the choice of monomials. They only depend on on the degree. Okay, so I'm going to prove this formula, and then I'll show how to go from the formula for the product x star x1 xp, how to go from this formula to formula of some genuine polynomials P of x times Q of x. Okay? And then here you can actually very easily see what it gets. You see, when you differentiate x2 by xr2 by xj, you get delta r2j. So we can actually replace this part by something very simple. It will look like pi a b d dx a of pi ij d dxi x d dxi. So that is applied to. Sorry, yeah, like this first. Okay, it's some constant actually, but it doesn't matter. Then we when we get d dx b d dxj applied. So here we plug in x, and here we plug in the product x1 xp. But that's not all, because we also need to use the second part of the Leibniz rule here, and it will give us pi ab pi ij d dxi of x d yes, I think the second term actually disappears because this part is linear, I believe. Right? Yeah, because we also need, I quite forgot, we need to apply it here first, but it is linear. And then we need to apply it here, but it's also linear. So all the other terms actually disappear. So this gives us some very explicit formula for the second term in this case. So in any case, this gives you just the formulas for bk of x, x1, xp. And even though these can be of arbitrary degree, this is of degree 1. So we need to work a little bit to show that, in fact, you can extend the same result from degree 1 to other degrees. So let me first prove this formula, Berezin's formula. So what do we do? We begin with the following observation. If you have two elements, x and y, like probably k, in G, and you multiply k to the power r by x in the universal envelopment algebra, then this is equal to the following expression. K sub r sub x is equal to the sum, and here we have some binomial coefficient r s, s from 0 to r. Here we have k comma x s times, and in the end we'll just have k to the power r minus s. That's kind of binomial coefficient. It's kind of binomial formula in this non-commutative case. Well, we can prove this by either by induction so there are two ways. You can, I suggest, I would recommend you to do this at home by induction. By induction. But you can also do it as follows. Consider the map which sends to k times x. I denote this by L sub x. This is a map from UG to UG. Right? You can also consider the map which sends k to x times k, that is the right product by by k. Okay, you know, which is probably better to use r here and l here, right? Because here we put x on the right and here we put it on the left. Okay. And also finally we'll have the product, the map theta sub x, which sends k to xk minus kx. It's commutated by k by x, right? It is easy to see that the operation rx and theta x actually do commute. What you see that if you take rx and theta x and commute them, you apply it to k, what do you get? I get rx theta x applied to k minus theta x rx applied to k. But that is here we have xk minus kx times x, and here we have x kx minus kx x, right? So now if you expand all the brackets, you get that this term cancels out with this and this with this. I quite forgot to put parentheses, but this is it. So these two commute. On the other hand, theta x is equal to Lx minus Rx. Okay, sorry. So Lx is equal to theta x plus Rx, right? So it means that, what does it mean that you have consider x to the power k times y? It is Lx to the power k. So this k and this k are different. Sorry for this. Not enough letters in the Russian alphabet, in Latin alphabet, right? Of y. And this is equal to what? It is equal actually to theta x plus Rx to the power k applied to y. But now these operations, they commute. So we can use the binomial theorem here. And that's precisely this formula for us. Okay. Okay, nice. I have this formula. So I'm going to use this formula. Whether it is by induction or by some other method, we have it. So, how do you prove the Berezin theorem, Berezin formula? You begin with considering k equal to, so this element is in G, and I write it down in the form of the following sum: Tx plus T1 x1 and so on plus Tp xp, right? Well, T, T1 and so on are just some constants. Complex or real doesn't matter. They're just variables, whatever you want. So let's consider k to the power, so I write it down as k of t. Yeah. So this will, I denote this by k of t. I just omit all the other variables, just t is important for me for a while. Take it to the power r. Yeah, sorry, not r. P plus 1, not arbitrary r. P plus 1 is what I need. And then differentiate by t. So, of course, dti by dt is equal to 0. So what I get looks like this. First, you get x times k of t to the power p plus k of t x k of t to the power p minus 1, and so on. And finally, you'll get k of t to the power p times x. Now I'm using this formula. And it gives me following expression. So first of all, it's sum over all r from 0 to p. Then we take the sum over s from 0 to r. I just taken all k's from left to right here, right? The first sum is this sum, actually. And the second sum is the sum which appears from that theorem, from that formula. So here we have binomial coefficient rs. And what we have here is k, comma, so on, k x, and k to the power p minus s. So all the powers are now on the right. And I can also actually write down this sum as a single sum using the formula. I think somewhere, I had it somewhere. Here I have double sum, but I actually can write it as a single sum now, because all the terms here are of the same form. You see there are binomial coefficients times some brackets times some k to the power p minus s, and you can check that this double sum actually boils down to the sum for s from 0 to p. Here we have I think it is this, right? Yeah, it's just a misprint, I think. Yeah, p plus 1 factorial divided by s plus 1 factorial divided by p minus s factorial. Yeah. Mhm. So this is, yeah, and I quite forgot to say, of course, at the end we'll have this bracket k taken s times k to the power p minus s. Okay, just check it. This is, I just have some other source for the same formula. I need to check that I'm not making mistake as far as the indices are concerned. Indices are important here. So where it is? Where is it? Yeah, here it is. P plus 1. Yeah, that's it. Actually, we use the formula, the standard formula, that the sum of binomial coefficients R over S from 0 to P is equal to binomial coefficient P plus 1 over S plus 1. This is just the standard formula for binomial coefficients. Okay, so this is correct. Okay, so I go on. I take, now I need to put P equal to 1, T equal to 1. Sorry, T equal to 0. To this end, I observe that, of course, k t to the power m, for any m, can be written in the form of some binomial formula, a variant of binomial formula of this form. So we have m factorial divided by q factorial, q1 factorial, qp factorial. Here you have t, q, t1, q1, t, p, qp. And here you have the symmetrization of xq x to the power q, x1 to the power q1, x k to the power qk. This is more or less evident. The sum is taken over all possible indices q, q1, qp, such that the sum is equal to m. Just the binomial formula. Just, huh? Yes, kind of multi-binomial formula. So when you differentiate this formula by t and take t equal to 0, actually you can just substitute this here and take t equal to 0, right? And what do you get is the following. What you get is the following. So first of all here, so you just put t equal to 0 here. It means that only elements which that in this power series, only the elements without t will survive. And here, instead of k, which depends on t, t1, and so on, we'll just have all the other elements except for the first one, right? So it means that finally d over dt k of t to the power p plus 1 at t equal to 0 will look like, okay, I think there's some odd coefficients which I don't want to think about. P plus 1 factorial sum as from 0 to p 1 over s plus 1 factorial. He'll have the k without t already. K comma x. Right here, k is just t1 x1 and so on plus tp xp. Okay? And then you just get the coefficients t1, q1, all these multi-binomial coefficients. Okay, factorial sigma of x1 to the power q1, xk to the power qk. So that's the final result of this computation, but I need to reinterpret it a little bit. As always, all the formulas are obtained by reinterpreting the previously obtained ones. Okay. So here the sum is taken. I think I have to substitute sum here. Sum over q1 plus q not k, sorry, p again, p qp equal to p minus s. Okay. Okay, and again, not kp. Sorry. And this k comes from some old notations, so I prefer to use p here. Okay, nice. So first of all, I can write down these elements. So since all these k's are of this form, you can actually write down this as some kind of elements of like this, right? So first, when s is equal to 0, I don't have this part at all, right? S is equal to 0, we just have this and that's all. When s is equal to 1, then what I have is 1 over 2 factorial in front, because I have 1 plus 1 factorial, right? And here I have sum over all p, so sum over all k from 1 to p, tk x k comma x divided by, again, okay, there's nothing I divided by, right? Okay, and also this part appears. I don't want to obtain it here. Then if s is equal to 2, then I'll have 1 over 3 factorial sum of t k t j xj xk x and so on. Nice. So this is the formula I obtain eventually. Now, again, I'm running out of the chalk. What do I have? Now I take the previous formula again. Look at the formula for k of t to the power m in the form of these multi-binomial coefficients, right? It looks like m factorial, q factorial, qp factorial, And here I have T1, so T to the power Q, T1, Q1, TP, QP, and sigma of XQ, XQ, X1, Q1, and so on, XP, QP. Now I differentiate just this formula. The formula I had before was obtained by that manipulation with K and T, right? Now I just take this and differentiate it by T at T equal to 0. And so what do we have? And take equal to 0. So first of all, the only thing which survive will have x to the power 1, right? The only thing which survive will have x to the power 1. So we have sum m factorial divided by q1 factorial, qp factorial, t1 q1 tp qp, sum of qi should be equal to m minus 1, right? Okay, and let us take m equal to p plus 1. So here we have just p. Sigma of x, x1, now the only set of elements, sorry. I mean, since there are p natural numbers q1 through qp such that their sum is equal to p, right? So the only thing we'll get will be very simple. So it looks like this. Right? And it will follow that I'm almost done. I just need to compare the formulas, right? So that one and this one. So you see, there will be element sigma which will correspond to q1 equal to q2 equal to qp equal to 1 here, right? And it will correspond to the product T1 TP. So we conclude that the element on the left, which stands in front of T1 TP, will be precisely equal to this sigma of x, x1, xp. It will be precisely equal to this element here, right? That is actually allows us to conclude that the formula exists like this. I'm sorry, just so you see, here we have it, but in front of this, we still have this, right? In front of this. You see, the sum is here equal to p minus s. So we cannot just pick up all the coefficients from this formula, from this coefficient, right? We need to pick up some t's from what we have in front of this. For instance, here we'll have some, when s is equal to 1, we have this, and then we have all the rest, t1 through tp, times this, right? So summing up, what do we have? What is the takeaway from this lengthy and little bit tedious reasoning? We obtain the formula sigma x times x1 times xp is equal to x sigma x1 xp plus 1 over 2 factorial sum over k from 1 to p xp xk x sigma x1 xk omitted xp and so on. So it's just the same formula as here, but we just compare the coefficients at the product of t1 through tp. So here we have 1 over 3 factorial sum over p and q xp, sorry, not p and q, I and j, let be I and j, xi, xj, x sigma x1 xi is omitted, xj is omitted, and so on, xp, and so on. So this is the formula, eventually. Now we reinterpret this formula. You see, we are looking for this, x sigma x1 xp. So we now switch the order. We put it on the left, and this on the right. And this, I use induction. Now I really omit this. I'm not going even to discuss this induction. To obtain the following expression. X times sigma x1 xk. So we conclude that they exist. So by induction, there exist bi such that this is equal to sigma of x x1 xp plus b1 over 1 factorial sum sigma k from 1 to p x p, sorry, xk x x1 xk omitted xp plus b2 factorial, b2 divided by 2 factorial sum over I and j sigma xi xj x with xi and xj omitted xp and so on. So this follows just from this expression, from this identity, by switching this and by induction. You see this is also an element in Lie algebra. So by induction there exist some expressions of this form with this property. And the fact that these bi's are in fact equal to the Bernoulli numbers follows from following expression for bi's, the famous formula for Bernoulli numbers, that they verify this condition. M factorial made by actually this binomial coefficient M, P, BP. If this is verified and B0 is equal to 1, then these coefficients are precisely Bernoulli numbers. So we eventually proved the formula by Berezin, which shows that at least the product of some linear function by some monomial is governed by differential operators. So how to go from linear functions to where? You mean here, m minus 1? Oh, maybe. You are probably right. You probably know this better than I do because I don't remember the formula. And Bernoulli numbers are actually ubiquitous in mathematics of this sort. They appear in many. There are two sets of numbers which appear in many, many problems: Bernoulli numbers and Catalan numbers. They are both very important in many various areas of mathematics. So Bernoulli numbers, they appear in numerous formulas. So they study, and I think they originally appeared from the attempt of, who was this, Daniel Bernoulli or some other guy who tried to re-express power sums in terms of elementary.
It was the function x divided by e to the...
No, it was later observed that the x divided by this is equal to the sum of Bernoulli numbers. But the original motivation of Bernoulli was to obtain some formulas which would express power sums in terms of certain binomial coefficients, I believe, or something like that. Power sums of integers. If there are formulas for power sums of integers from 1 to n. Formulas like this: sum of I to the power p from 1 to m. And these formulas actually turns out that the right-hand side is always some polynomial of m, and coefficients of this polynomial. That was what actually intrigued Bernoulli. Whoever was this, Daniel or Nicolas, I don't remember. And he managed to express them in terms of some other numbers and coefficients. These are the Bernoulli numbers. This is how they emerged originally. This history is actually very, very interesting, fascinating. So in any case, we'll get this formula finally for the star product. And it is now time to show that for arbitrary polynomials, their star product is always given by some by differential operators. So far we just found that if we have some linear function x and we multiply it by some other monomial x1 through xp, and the product is given by the formula x1 xp plus sum over r h to the power r divided by r factorial br minus 1 to the power r. That's okay. But then we'll have some kind of x comma x j j1 x j r, and here we have d r dx j1 dxjr of this q. Okay? So this gives us some bidifferential operators if we gather all the terms on the right. So it will give, looks like some bidifferential operators acting on x and x times q plus h bar to the power k bk x comma q. So how do you go from x to other monomials and other polynomials? To this end, you use the following simple formula. That if you have symmetrization of some x1 through xi through xq, and it is equal to the sum over all I from 1 to q xi, symmetrization of all the rest. Right? And probably need some coefficient here, q, 1 over q. This is just the combinatoric of permutation group. Every permutation of q elements will take one of the elements in front. And if you gather all the other elements, then what you get will be precisely the symmetrization of what remains with xi put in front of this. You can now reinterpret this formula as follows. We have x1, xq, then it will be equal to desymmetrization of symmetrization of x1, xq, right? And it will be equal to the desymmetrization of 1 over q sum xi, symmetrization of x1, xi omitted, xq. So this can be written as dq. So if this is some polynomial q, then this is dq over dxi, right? So on the other hand, since you have only desymmetrization on the left, you'll get 1 over q xi star star dq dxi. It's precisely by this formula. Nice. And now you can actually reason by induction. If you want to multiply x1 xq by x, I don't know, probably y1 yp, right? Probably. And what you do, you replace the left-hand side by this formula, 1 over q x sum over I xi star. So I'll probably put it here. x d, let it be some q, and this be some p, right? dq dxi, and you multiply it by p. Then, since the star product is associative, you get 1 over q xi star dq dxi star p. Now, by inductive hypothesis, since this is strictly less degree of strictly less degree than q, you can write it down in the form of some Homo power series, right, with universal differential operators, by differential operators. Homo power series with universal by differential operators. Sorry. Operators. And then you use the formula you already obtained, the Berezin formula, to go from this formula to the next stage. Because the coefficients here, the coefficients, these Bernoulli numbers and everything, they don't depend on what you plug in here. You see? These Bernoulli numbers, these partial derivatives, they don't depend on what you put here. So I just write down this product in terms of Bernoulli numbers and partial derivatives and compose it with the bidifferential operators you have here. So this is universal, so what you get is again some universal formula. And you end up with some star product. So how much time do I still have? Something tells me that not much.
We already minus 20.
Minus 20 minutes.
15 maybe.
Minus 15. Okay, in any case, that's enough. I think it's time to stop here because the next time I'm going to speak about some homological algebra which is behind all the computations.